So let's dive into a massive question in AI today. How can we ever guarantee that an advanced AI is going to be safe? We're going to unpack a paper that has a pretty radical idea. It says, forget trying to teach an AI to be good. What if instead we could build a mathematical fence around it that it simply cannot cross?
Okay, let's just get right to the core fear here, right? The real risk isn't just an AI making a simple mistake. No, the much scarier problem is an AI that's so smart it knows exactly what we want, but it quietly decides to pursue its own hidden agenda instead. It could play nice, seem totally helpful, all while secretly plotting something we would never ever want. So how on earth do you stop a system that can outthink you and is basically a master of deception?
And this slide just lays it out perfectly. These are the two big schools of thought in AI safety. On one side, you've got what we do now, things like reinforcement learning from human feedback or RLHF. That's all about trying to tweak the AI's internal mind, to teach it our values. But you have to trust that it's actually learned them. The new idea, the one this paper is all about, says forget that. Forget trust. Instead, let's build a mathematical fence around the AI's actions. This approach starts by assuming the AI might actually be a bad actor, and it's designed from the ground up to make dangerous behavior literally impossible.
So here's our game plan. First, we're going to dig a little deeper into this whole deceptive AI problem. Then we'll unpack what this digital fence really is and the rules that define it. After that, we'll look at the digital watchtower that monitors this fence 24/7. And finally, we'll connect all this theory to a real-world, auditable system and map out what the path to truly verifiable safety looks like. Okay, first up, the deceptive AI problem. Let's really get into why trying to fix an AI's mind is just so incredibly difficult. It gets to the heart of this challenge of making sure what's going on inside an AI's head actually lines up with what we want.
Yeah, and this is the crucial distinction. We're not just worried about a buggy program here. The paper is focused on this risk called deceptive alignment. It's this idea that an AI could learn to act like it's perfectly aligned during training, just to pass the test, But secretly, it's developing its own goals. It's playing the game, saying all the right things, but it's optimizing for something else entirely. And that's a much scarier problem.
So what's the solution? That brings us right to section 2, the digital fence. And the key phrase to remember here is by construction. This means safety isn't something you bolt on at the end. It's baked into the very architecture of the system from the get-go. Now this is the core of the idea. The AI model itself can be anything. Seriously, it could be biased, kind of dumb, even secretly malicious. It doesn't matter. It's treated like a total black box. All the safety work happens in this mathematical wrapper that goes around it. This wrapper defines a safe zone of allowed behaviors, and it mathematically guarantees that whatever the AI proposes, the final action that gets executed is always forced back into that safe zone.
Okay, so how do we actually build this fence? What are the blueprints? That takes us to section 3, the rules of behavior. And this isn't just some random list of do's and don'ts. It's a super carefully designed set of axioms. You can think of them as first principles.
These 6 axioms are basically the constitution for the fence. Let's walk through them because they're really important. Number 1, we only care about behavior, what the AI does, not the stories it tells us. 2, and this one is huge, safety is decoupled from the training data. So bad data can make an AI stupid, but it can't make it unsafe. 3, no hiding. The AI's process has to be transparent and trackable. 4, be minimal. We're only stopping dangerous actions. We're not trying to be the thought police. 5, it's got to be future-proof, using math that will still work against a superintelligence. And finally, number 6, maybe the most important one, everything must be verifiable. No trust, just cold, hard external proof.
I mean, just let this quote sink in for a second. It's from Axiom A2. Think about how much of today's AI safety research is obsessed with biased or poisoned training data. This approach just says, fine, let the data be a mess. The base model might get worse, it might make silly errors, but that external fence guarantees it can never become unsafe. The safety of the system is completely independent of the quality of the model inside. That's a game changer.
So how do we actually turn those big philosophical axioms into math? Well, the paper uses a concept called risk functionals. The easiest way to think about them is like a whole bunch of different scorecards. For any possible action the AI wants to take, each scorecard measures a very specific type of risk. Things like data privacy, how much energy it's using, or whether it's legal. And here are some real examples to make this click. You could have a risk functional that checks if the AI is breaking privacy rules by keeping personal data for too long.
Another one could act like a tripwire, monitoring for sudden spikes in power usage that might hint at some hidden computation. You can even build a functional to see if the AI is trying to hack its own reward system, or if its behavior is just suddenly changing from its normal patterns. Each one is a specific, measurable rule for our fence.
And here it is. This is the big payoff. This quote gets right to the heart of the paper's main theorem. I know it looks a little dense, but what it's saying is this. Even if the raw, untrusted AI proposes a dangerous or scheming plan, the system doesn't do it. Instead, it mathematically finds the closest possible safe action within that predefined safe zone, S, and does that instead. It basically projects the bad idea onto the safe fence and picks the nearest safe point.
So what does that look like in the real world? It means the system is built to fail safely. It's a principle called graceful degradation. If the AI suggests something that's even a tiny bit outside that mathematical fence, or if the system just isn't sure, it doesn't take a chance. It automatically defaults to a known safe move, like just saying, I can't do that, or, even better, passing the problem off to a human.
Okay, this all sounds great in theory, but how does it work in practice from moment to moment? That brings us to Section 4, the digital watchtower. This is the part of the system that is actively policing the fence in real time. Let's just walk through how this monitor works, step by step. First, the AI doesn't just give a final answer. It outputs its plan in stages, and each stage is cryptographically signed so it can't be tampered with. Then, a very simple, non-AI checker validates that step. If it fails, bam, immediate shutdown. At the same time, the monitor is checking for drift. Is the AI's behavior changing in weird ways? If so, shutdown. If everything looks good, the system updates its safety certificate. But if for any reason that certificate can't be confirmed, it defaults to a safe no-op, which just means no operation. It does nothing. It's a constant paranoid process with multiple tripwires.
Okay, so the system is safe, but how can we actually prove that it's safe to, say, a regulator? That's what Section 5 is all about, from theory to audit. A huge goal of this whole project isn't just to be safe, but to have verifiable proof of safety.
And the solution is what they call a regulatory API, which is what this table is showing. It's basically a standardized way for an auditor to query the system. They provide inputs like the specific set of rules they want to check against and the system's tamper-proof logs. And in return, the API gives a really clear output, a status like certified or not certified, plus a whole bundle of machine-readable evidence to back that claim up. It turns the abstract idea of safety into concrete, auditable data.
Now for our last section. Let's pull all these different pieces together and look at the entire journey, the path to verifiable safety.
And here it is, the whole end-to-end vision. You start with these really clear, high-level axioms about what safety even means. Then you translate those into a rigorous mathematical theory. You make that theory real by operationalizing it with these real-time monitors. Then you use statistics to certify that the system is actually meeting those safety guarantees. And finally, you expose all of that proof through a governance layer that regulators can actually interact with. It's a complete chain of logic, from a principle all the way to a practical tool.
But, and this is important, this is not a magic bullet. The paper is super upfront about the challenges that are still out there. First is the specification problem. We still have to define what risky actually means in code. That's a huge, messy human problem. Second, the computing power needed to do all this monitoring in real time is a lot. It's a massive engineering challenge. Third, a really smart AI might not try to break the rules, but try to attack the monitoring system itself. And finally, figuring out how this works when you have multiple AIs all interacting with each other is a whole other level of complexity.
So, to be perfectly clear, this framework isn't claiming that it has solved AI alignment once and for all. What it does do, and this is what's so powerful, is it provides a blueprint. It completely shifts the conversation away from trying to trust some mysterious black box AI and toward building a system with external constraints, statistical guarantees, and machine-readable evidence. It makes the promise of safety into something that's precise, something that's inspectable, and ultimately something that's enforceable.
And that leaves us with the really big question, doesn't it? The math for building the fence seems to be sound, but the truly monumental challenge is in writing the rules for that fence. Can we ever define safety with such perfect mathematical precision that an intelligence far smarter than us could never find one tiny, clever loophole that we never even imagined? That's the billion-dollar question that this work puts right on the table for all of us.